Okay, good morning, afternoon, or evening, everybody. Welcome to the Earth's Energy Balance, NASA ASDC's role in advancing PREFIRE's insights on polar radiation, ASDC data training webinar. This is your host, Jennifer Brennan. It is 2:30 p.m. Eastern Time, so we're going to go ahead and get started here. What I'd like to do first is begin today's webinar with a few logistics. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A panel rather than the chat, and you should see this located on the right side of your screen. If you don't see the Q&A panel, you can click on the three dots at the bottom of your screen to pull up your panel options and then insert a check mark next to the Q&A option. A quick word about the chat. Participants will have the capability to chat with the hosts and the presenters, but not with all participants. So again, if you have any questions, we'd like for you to enter those into the Q&A panel on the right side of your screen so that everyone can benefit from those questions. Okay, today's webinar is being recorded. The recording will be made available online within a week of completion. Once completed, what I will do on my end is send an email to all registrants and participants that includes links to both the recording and presentation slide decks used within today's webinar. In terms of timing, today's webinar will be 2 hours long with 1.5 hours allocated to the presentations and demonstrations. A 15-minute Q&A period will follow, and depending on the volume of questions we receive, we may extend the Q&A session, but we will have a hard cutoff of 4:30 p.m. Eastern Time. And let me advance the slide here. During this afternoon's webinar, we have 3 speakers. Our first speaker is Dr. Hazem Mahmood. He is the science lead at NASA's Atmospheric Science Data Center, or ASDC. Our second speaker this afternoon is Elizabeth Joyner. Elizabeth is a product owner for the Satellite Science Mission Support Team and also the Science Outreach Lead at NASA's ASDC. Our third speaker this afternoon is Dr. Brian Druin. Brian is the Deputy Principal Investigator for NASA's PREFIRE mission at the Jet Propulsion Laboratory, or JPL. Through today's webinar, our speakers will take you through a series of topics, including webinar resource guide, atmospheric science data center overview, a PREFIRE mission background, PREFIRE data overview, and a series of demonstrations for discovering, accessing, and working with PREFIRE data. Speakers will also provide you with some data learning resources to support your workflow. Once everyone has finished with their presentations, I will open it up for a couple of final optional polling questions and a Q&A session. Before I toss it over to Hazem, though, I do want to say just a couple of words about this afternoon's Q&A session. We'll try to answer all of the questions within the time allotted, but if we are not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. So with that, it is my pleasure to introduce today's first speaker, Dr. Hazem Mahmood. And Hazem, at this point, let me stop sharing my screen and I can toss it over to you. All right. You're quite welcome.
Thank you, Jennifer. Good morning, afternoon, evening, everyone, and welcome to today's webinar, Illuminating Earth's Energy Balance, ASDC's role in advancing PREFIRE's insights on polar radiation. My name is Hazem Mahmood, ASDC back scientist. I am joined today by Brian Druin, Deputy Principal Investigator and PREFIRE Project Scientist, and Elizabeth Joyner, our outreach lead at the ASDC. Elizabeth and I both supporting NASA's Atmospheric Science Data Center under research contract, and Brian is from NASA JPL. The PREFIRE mission represents a groundbreaking step forward in understanding the Earth's radiation budget, particularly in the polar regions, where climate change impacts are most pronounced. Over the next couple hours, we will take you on a journey from fundamental science behind PREFIRE to hands-on demonstration of how we can access and work with this revolutionary data. Now, I will give it over to Elizabeth to walk us through the agenda. Over for you, Rose.
Thank you so much, Hazem. Let me walk us through what we have planned for the next 2 hours. Our agenda is to take you from foundational knowledge to hands-on application. We will start with a guide to keep you organized and connected to our resources, and then we will offer an ASDC overview where we will introduce you to the Atmospheric Science Data Center, who we are, what we do, and how we serve the earth science community. Next, we will dive into the mission background, where Brian Druin will explain the science behind this mission, why polar radiation measurements matter for understanding Earth's energy balance, and what makes PREFIRE so innovative. Then we move into the practical applications with PREFIRE data in the cloud. We'll show you how these data live in NASA's cloud infrastructure and what that means for your research workflows. Our tools and services section will be highly interactive. We'll demonstrate multiple ways to access and work with PREFIRE data, from cloud-based visualization tools like Worldview to data discovery through Earthdata Search to integration with GIS platforms like QGIS and ArcGIS Pro. One of the highlights will be our live Jupyter Notebook demonstration, where we'll show you a very simple step-by-step how to programmatically access PREFIRE using Python and earthaccess library. Perfect for researchers who want to integrate these data into your own analysis workflows. We'll wrap up with PREFIRE Resources to help you continue your work beyond today's session, and of course, plenty of time for Q&A, as Jennifer mentioned throughout. Ready to dive in? Let's start with learning about the ASDC. Jennifer or Joseph, would you please share the Zenodo link in the chat? Throughout today's session, we will present a comprehensive overview of NASA's Earth data resources. For your convenience, we have compiled all of the showcased resources along with supplementary materials in a Zenodo repository. Please use the provided QR code or URL to access this documentation at your convenience. Just note that it is there for you. Also note that you will need to access version 2 of this repository to access both of the presentations featured in today's event. Next slide. We support PREFIRE because we are part of NASA's Earth Science Data and Information System, and it is the NASA's infrastructure for all data archiving and distribution. At the core of the ASDC system is the Distributed Active Archive Centers. There are 11 of these DACs, or data centers, distributed across the country, each focusing on a science domain, and as you can see where they are here on the map. Other elements are science data processing segments. Together, our federated system of processes, archives, and distributes thousands of data products to the global user community. And we also offer user support and services to help them in their journey with our data and tools. We also offer benefits to the science community, such as supports to metadata development, metrics, and tracking. Haslam and I join you from the Atmospheric Science Data Center, also we call the ASDC, shown in yellow here, in Hampton, Virginia, which is situated at Langley Research Center, NASA's first center and home to the nation's first civilian aeronautics lab. This is where I am the outreach lead and product owner of the Satellite Mission Support Team, and Haslam is our incredibly talented data center scientist. Next slide. ASDC specializes in atmospheric science data, including radiation budget, cloud dynamics, aerosols, and tropospheric composition. We support over 100 science projects, including PREFIRE, Tempo, MISR, MOPPET, Ceres, Calypso, and Maya, plus airborne validation campaigns. Last year alone, we managed over 3,000 unique science products, serving over 4.6 petabytes to over 160,000 users across 158 countries. Our archive contains 8+ petabytes and 168 million files. The ASDC has a lot of data, and these data are growing fast, especially as we transition to scalable cloud infrastructure, dramatically improving researcher access to large data sets like PREFIRE. ASDC operates on 5 pillars: ingest data from providers and missions, archive for long-term preservation, distribute through tools and services, processes to create higher-level products, and engages users through outreach and support to maximize research community impact. Now I will pass it over to Haslam.
All right, thanks, Elizabeth. Now we have covered the ASDC roles and capabilities. It's time to dive deep in the heart of today's presentation, the PREFIRE mission itself. We're excited to be joined today by Dr. Brian Dorn, who will walk us through the mission scientific objectives. Brian, please take it away.
Thank you, Hazen. So, yes, as I said, my name is Brian Druin. I'm representing the PI, and I also run the science team for PREFIRE. The science team is shown on this chart, and we will be going through the background of how we got PREFIRE started. The radiation balance of the planet is, based in a nutshell, the balance of the incoming energy from the sun and then the energy radiated out into space as heat. And any imbalance in that budget is what we call climate change. And that the whole system interacts pretty strongly. We see most of the solar radiation coming in near the equator, and then weather and ocean currents move that energy around, and we see emission from all over the globe at longer wavelengths. However, that emission in many cases is trapped by the wet atmospheric greenhouse effect. So most people are familiar with carbon dioxide absorbing the thermal radiation, and that's the greenhouse effect that's changing from fossil fuel burning. However, the greenhouse effect that keeps our planet near room temperature is largely due to the water vapor in the atmosphere. We're a water planet, and most of the planet is very wet, so the longer wavelengths get blocked and trapped, and what you see looking down from space is the cold top of the atmosphere rather than the surface. However, this is not exactly true in the driest parts of the planet, which is where you see snow and ice year-round, like at the poles. The water vapor is condensing down to the surface, and in these regions, the longer wavelengths more efficiently escape into space, and that's what we call the OLR, the outgoing long-wave radiation. And there's significant uncertainty in the OLR at these longer wavelengths because there has not been systematic measurements except for broadband across the spectrum integrations from instruments like Ceres that you can also get the data from ASDC for. So we petitioned NASA to support us in a low-cost effort to put up 2 spectrometers to start cataloging and getting the metrics of this outgoing radiation so that we could tie it to the processes that we can observe in many ways from other sensors. And this, of course, matters for balance of energy at the poles, where we're seeing the ice melting rapidly, but that ice melting, it's not just a polar situation. There's a global impact in that the melting ice is causing a significant amount of the sea level rise that is being observed. And we also know that this energy balance is largely the ocean currents and the weather systems are distributing the heat to the poles. And if the poles become less efficient at emitting that heat out into space, that means that the energy gets trapped in the Earth system for longer, which then drives more extreme weather and climate. And so when you hear that the theories about climate show increasing sea level and increasing weather severity, those are both directly linked to what's happening at the Earth's poles. And so we propose to put up 2 small satellites, CubeSats, to observe the Earth from pole to pole, and crucially to extend spectral measurements that have traditionally been only done at shorter wavelengths for technological reasons. We've used a very simple technology, not very sensitive, to extend the spectral range out from 15 microns out to 50, so that we can pick up in about 50 different channels this outgoing radiation and understand just how much of it is getting absorbed by trace amounts of water vapor at the poles. So about 1.5 years ago, we we're able to get our hardware launched into space. We got checked out on HAT2 was launched first. That one needed a little bit more care and got ready a month later. And both of these satellites contain a thermal infrared spectrometer, and the view of the Earth is making measurements in a push broom format where we see 8 different scenes on the ground below the satellite. And then periodically through each orbit, we take a look at cold space and a known temperature target inside the instrument that allows us to change the response of the instrument into a calibrated radiance based on the understanding of our calibration target. And this is then allows us to produce a level 1B radiance product. And our science for the prime mission has been focused on the Arctic and the Antarctic, where we're getting about 100,000 measurements each day for each of the satellites. The 2 satellites are in different phase orbits. They're a little bit more than 4 hours in separation, and that separation in time is growing as their altitude decreases. They're not decreasing at the same rate, and so the ground footprint is changing by a small amount and the time separation is changing by a small amount. But this is good because what we wanted was a variety of different time of day sampling, and we're getting that as expected. So here's the launch dates, and you can see the time separation in the 2 launches. That speaks to their separation in orbit. And the hardware is not that big. This is about the size of your laptop and a little bit thicker. The solar panels unfold to about 1.4 meters size. This is a trick that we could pull off getting such a capable sensor into such a small package. We did that using room temperature detection technologies. And now that we're getting those measurements, we're doing the observations of the far infrared at both poles. That's helping us test these 2 hypotheses, which are coupling the observations to models of Earth systems. So the first hypothesis is that the time-varying errors in the far infrared emissivity and atmospheric greenhouse effect are biasing estimates of the energy balance. The balance between the surface and the atmosphere is likely not quite right in the models. We have underpredicted the rate of climate change at the poles historically, and so we expect to be able to see the reasons for that underprediction in our data when we compare them to the models, and that this might then explain a large fraction of the spread in the projected rates of Arctic warming and the associated sea ice loss, ice sheet melt, and sea level rise. So we're able to, by informing the models and allowing systematic improvement to those models, we expect to be able to better predict the future state of our planet. And specifically, our team includes the ice sheet system model component, which has got a detailed analysis of all the glacier ice in Greenland and Antarctica. And we're working on layering in more spectrally dependent physics about its energy exchange with the atmosphere. And then separately, we have the Community Earth System Model framework that is looking at Earth as a whole, and we're able to plug in various modules that are affected by the far infrared balance there. And so a little bit about getting the project going. We, in orbit checkout, we're looking carefully at the radiances at the shorter wavelengths to line them up with infrared imaging from sensors in geosynchronous orbit, where you fly right under them and you can make a similar measurement at that wavelength, and then use things like the coastline here at Hudson's Bay as a nice strict requirement for your ground track location. And we found that we were getting some systematic differences, and we ended up not relying on our onboard GPS, which for Satellite 1 was never functional, and in Satellite 2 it failed after a few months on orbit. This is one of the worst times for space weather to be flying. They're dealing with a lot of solar radiation at solar maximum. But we were able to do a geolocation to better than 25 kilometers, estimate 2 to 12 kilometers along track and 2 kilometers cross track, based on radar measurements of our spacecraft positions, which are otherwise known as two-line elements. These are what are used for tracking satellites on the ground. And we feed that information into our algorithm to do our geolocation as a matter of course now. And this just goes into some detail about what our ground tracks look like. We have 8 sensors across the focal plane array that each give you a spectrum, and they are not close packed on the sensor array, which means that there's gaps between the scenes on the ground that are about 2 pixels wide. So you can see a ground track where we've zoomed in on the Arctic, and there's the 8 scenes running from lower right to upper left. And then there's this gap here. That's one of our calibration sequences where we spend about a half a minute or less looking at cold space and our internal target. We do not make Earth measurements during that time. Those are not synchronized with any of our flights, so they tend to move around and not obstruct any one spot on the globe. And then if you zoom in at the footprint scale here at the edge of one of these calibration scenes, you can see that we actually have overlapping scenery in the along track direction. So what's colored in dark blue here, that's the length of a single frame superimposed over the oversampled imagery. Every 0.7 seconds, we get another measurement. And so there is some overlap of information from one measurement to the next in the along track direction. Visualizing the spectral data in across a map, it can be challenging. So what we've done on the right-hand side is taken a portion of the spectrum. This is from about 11 microns to 22 microns. So from the traditional IR window into the dirty window where water vapor can strongly absorb in a wet atmosphere. And we've converted the radiance to a brightness temperature. So you can think of it as something reflective of what the Earth emission is like at a given wavelength. And in this particular sample, I'd taken one of the 8 scenes and wrapped it around for that orbit where we actually were able to observe about 100-degree difference in temperatures on the planet with that one part of the instrument. And over here in Southern California, where I am, it was 45 C that day. This was shortly after we launched. We were in the middle of a heat wave that was setting records in the Mojave Desert, which is saying something about global temperature. And on that same orbit, we were able to observe one of the coldest spots on the planet, the Dome Sea area in eastern Antarctica, where it was minus 55 C on the ground. And so when you look at the temperature in terms of the spectrum, you see that even though it was much hotter in the desert, when you get out to longer wavelengths, that actually look pretty similar in terms of the amount of radiation going out to space. And that is what we're talking about when in the wet greenhouse effect, that even though it's very hot and dry there, it's still much moister than what you see relatively in a cold, frozen area, where the Planck function is very similar to what you get for the surface temperature. Basically, there's no contrast between the atmosphere and the ground here in Antarctica. And so here, I mentioned the dirty window. That's essentially water vapor over here beyond 15 microns can very strongly absorb all of this far infrared radiation. And the fact that it doesn't do that in the drier times at the poles is what we're trying to get a handle on. And that can be a very strong function of a very small amount of water vapor. So we've been systematically measuring this since summer of 2024, and we're developing climatologies and using the information in process studies. Shown here is just a sampling of the climatologies for the radiances at two different wavelengths. 19 microns and 27 microns are both in the dirty window beyond 15 microns. And so you see that the temperature is representative of that cold, icy surface in the winter regions that not so strong in Greenland in the summer, but then you see it turn on in Greenland in the winter. And the extent of this and the effects with cloud cover are where we're seeing the variability in the signal, and that mean and variability are what we want to see the models track to when we get the improvements to the models in place. The models also give you a relatively pure version of the greenhouse effect that is been traditionally difficult to estimate without having the far infrared in the sampling range, but now with PREFIRE measurements, we can really talk about how much energy the atmosphere is absorbing at a given part of the planet. And these climatologies with respect to wavelength can be directly used in Earth system models. This is a climate prediction based on the coupled Earth system model, and they run it forward through time from the past to the present, and they actually have radiation going out at all these wavelengths over that time. When you project it into the present time, you can directly compare with PREFIRE observations. But of course, when you run the clock backwards like this, you can improve the metrics of the model and see if they're matching reality as you expect. And you can see the variability is different between 12, 14, and 20. That is to accentuate the change in how the small amounts of water vapor are affecting these surfaces in the Arctic. And then you see that there's a lack of contrast or change variability at 37 microns. And that's where the dirty window, at least in the Arctic, has closed. You might see action in the Antarctica out at those longer wavelengths because it does get even drier there. The data products that are available at ASDC are listed here along with points of contact. I am the point of contact for the level 0 and level 1B data products. And then we have co-investigators. Shanglei Huang and Aaron Morelli are at the University of Michigan. Brian Kahn is here at JPL, and Nathaniel Miller and Natasha Voss are at the PI institution, the University of Wisconsin-Madison. And Jennifer is providing contact information to people who attend this webinar so that you can reach out to us directly if you have questions about the data products. And like I said, this data is already available on the ASDC DAP. We've automated the transfer of new data, which comes in regularly, and we are in the process of working on an extended mission where there might be some growth in the types of products. So I'll stop there and hand back to Hazem.
Thank you, Brian. Going back to the slides here. Now let me walk you through slides. I'm just want to make sure that it's okay. Right. So now let me walk you all through how the PREFIRE data flow from measurement to distribution. So let me quickly show you eyes on Earth, eyes.nasa.gov/Earth. This is NASA Interactive 3D visualization tool that gives us a remarkable insight on NASA satellites. You can see here the solar system and Earth in real time with dozens of satellites orbiting our planet in different orbits. So let's start here. What you can see is the entire fleet of Earth observing satellites, each collecting unique data about our planet. Let me zoom in and locate our PREFIRE CubeSats here. So zooming in on the left, here you can see PREFIRE 2. Zooming more, here you go, PREFIRE 2. And then if I move to the right, you can see PREFIRE 1 right there. So these CubeSats make up the PREFIRE mission. What's remarkable about PREFIRE is the size, which each satellite is roughly the size of a shoebox, just 10 centimeters by 20 centimeters by 30 centimeters. So to put that into perspective, I'm adding a scientist standing next to the satellite or the CubeSat. Even with the compact size, these CubeSats carry sophisticated far infrared spectrometers that are revolutionizing how we measure Earth's radiation budget in polar region. Okay, following each PREFIRE path over Chile or Spain, PREFIRE transmits the data to the ground station using coded binary software. Subsequently, the PREFIRE team initiates the decoding to generate level 0 data and processing from level 0 to higher processing level 1, 2, and 3. In the Science Data Processing Center, or SDPC, at the University of Wisconsin, which is funded by NASA. This processed data is then ingested using ASDC's schemaless ingest system. The system archives the data permanently and ingests a public copy to the Earth Data Cloud using the Amazon Web Services, AWS. US West 2, which is located in the state of Oregon. Once the data is accessible, users can download it via Earthdata Search that we would be demonstrating later today. Additionally, users can subset the data using OPeNDAP and Harmony. Furthermore, visualization of the data is possible using tools like Worldview and GIS. PREFIRE integration with Amazon Web Service Cloud infrastructure opens up exciting possibilities for comprehensive data analysis. Users can leverage resources like Elastic Cloud Computing to perform advanced analytics and modeling. Data downloads are provided free of charge, as usual, allowing users the flexibility to choose their preferred computing environment, whether in local system or through cloud service provider. As always, the Earthdata Forum will be the best channel to address any questions, and we are committed to answer your question to help maximize the impact of the PREFIRE data. Now I'll give it over to Elizabeth.
Thanks so much, Hazem. It's great to learn about how all these data are available to access and put to use. But now we will segue over to learn what tools and services are available by NASA and our partners to access PREFIRE data. Thank you, Hazem. Jennifer or Joseph, would you please share this link in the chat? We mentioned the word distributed quite a bit, but we should mention that it's not synonymous with the term efficient use of or dissemination of these data. NASA offers many tools to help us access and get the most of our NASA Earth observing data, but finding the right tool for you and your research objectives may be tricky. This presentation will feature multiple tools for accessing and visualizing your data. I've highlighted here 5 tools and services that we will be showcasing today. Notice that each tool is not created equally. It is helpful to think about what kinds of data tasks you are trying to accomplish prior to getting started with any of these freely available tools and services. This chart I've created with Hasm's help over the last couple of years, help courtesy of Earthdata, to help us scope out our work and tools ahead of time. This guide is available in the Zenodo page provided. Next slide. Now let's talk about how you can actually access and work with PREFIRE data. As we demonstrated earlier with the tools you can use graphic, one of the strengths of NASA's Earth data ecosystem is that we provide multiple pathways to the same data, so you can choose the approach that best fits your research workflow and technical expertise. Starting with Earthdata Search, this is your go-to web interface for discovering and downloading PREFIRE datasets. It's perfect for exploring what's available, filtering by geographic region, time period, and other parameters, and downloading the files directly to your local system. Harmony Services represents NASA's next-generation cloud-based processing platform. With Harmony, you can subset, reformat, or even perform basic transformation on PREFIRE data before downloading, saving you time and bandwidth for getting exactly the data you need in the formats that you want. For programmatic access, we have OPeNDAP, the open source project for network data access protocol. This allows you to access specific portions of PREFIRE files directly through HTTP request, perfect for automated workflows and accessing just the variables or spatial regions that you need. Jupyter Notebooks provide an interactive environment where you can combine data access, analysis, and visualizations all in one place. We'll be doing a demonstration of this later, showing you how you can use the Python libraries like earthaccess to work with PREFIRE data. For our GIS users, PREFIRE data integrates seamlessly with ArcGIS Pro, allowing you to incorporate polar radiation measurements into your spatial analysis workflows. And throughout all of this, the Earthdata Forum serves as our community hub where you can ask questions, share code, and connect with other PREFIRE data users. And the beautiful thing is that all these tools are accessing the same high-quality PREFIRE data sets. You can choose the method that works best for your particular research needs. Thank you, Hasm. Let me break down the specific PREFIRE products and how they map to the services we just discussed. This table shows exactly what's available and through which platforms. We have 4 main product levels. Level 0 provides the basic orderable service. This is your raw auxiliary orbital telemetry data. Level 1 offers more advanced levels of service where data is available through Earthdata Search with thumbnail previews for quick browsing. Level 2 offers more comprehensive services with standard collections like the SATX2B products. Here you can find the core PREFIRE measurements, SFC for surface data, CLD for cloud properties, FLX for flux measurements, and MSK for mass data, and ATM for atmospheric profiles. These are available through Earthdata Search with thumbnails, and you can visualize OLR data directly in Worldview. For more advanced users, Harmony provides subsetting capabilities for using Level 2 subsetting or L2SS services and aggregation. Level 3 gives you fully processed, science-ready data. The SATX3 SFC sorted collection focuses on surface emissivity data, and you can subset these through Harmony OPeNDAP subsetter, also named OS service, and they are available for visualization as thumbnails. Notice how each product level offers different service options depending on your needs, whether you want to browse, download, individual files, visualize the data in web-based tools, or perform sophisticated subsetting and processing in the cloud. The key takeaway is that regardless of which PREFIRE product you're working with, you have multiple access and processing options. In our demonstrations, we will show you how these services work in practice, starting with the visualization capabilities and moving into more advanced programmatic access. Next slide. Before we get started with these tools, it is important to note that most of our tools and services require a freely and openly available Earthdata login. For more information about Earthdata login, please see the links in Zenodo. It is important to note that Earthdata login is not an account, nor is it an authentication. Now I'd like to pass it back to Hazem to get us started with our first tool, NASA Worldview.
Thank you. Now we are going to move from theory to practice. I'll take us through our first hands-on demonstration visualizing PREFIRE data using Worldview. This is where you will see how straightforward it is to visualize PREFIRE data through Worldview. I will show you step-by-step process of finding PREFIRE variable outgoing long-wave radiation. But first, Worldview and gives what it is. These tools are to make it easier for users to access Earth science imagery from computer or tablet or a phone, as you can see. Worldview also is an open source web mapping application where millions of users browse more than 1,000 NASA satellite imagery. GIBS or Global Image Browse Services is a set of services for imagery products for Worldview. So let's go worldview.earthdata.nasa.gov to see how to visualize PREFIRE. So as you can see here, this is the Worldview interface. On the right, you'll find an interactive display of Earth map, while the horizontal line down here in the bottom, where you can change the date and time, the display imagery. And on the left, you can explore and select layers of interest, as well as choose your preferred visualization mode. So to start, we'll go to this orange button on the left-hand side to search for PREFIRE. I'll type PREFIRE here in the search bar. Currently, we have 2 layers for each of the PREFIRE CubeSats. Once we add the 2 layers to the map, you can navigate through the data of interest and go to the horizontal bar in the bottom to change the date. The outgoing long-wave radiation or OLR color bar or color scale range from a minimum of 90 watts per square meter, shown in blue, to a maximum of 330 watts per square meter, shown in red. You will notice where the swaths intersect over the North Pole. So getting to this stage, I want to navigate to these layers and show you how customizable they are. For example, you can change the color palette of the layer for better visualization, or adjust its opacity to make overlapping data more visible. If you need to access the data in its native format, click on the top menu option to explore it as a cloud-optimized JPEG. You can see here it will redirect us to the Earthdata Search for download. As you can see, you can choose between SAT1 or SAT2, and then you will be able to move to the new tab in the Earthdata Search. So once you're on Earthdata Search, you can also visualize the granule by granule before downloading it, which is a great advantage. So you can see the variable before downloading it. We can also navigate into the map and change the visibility or opacity of the outgoing long-wave resolution. Right, now let's go back to Worldview to see another powerful feature in the layer information button. So by simply hovering over this I button on the left next to the layer, you can access the detailed abstract describing the specific data and its applications. Next, let's use the sliding comparison tool that is in the bottom here, analyzing outgoing long-wave radiation over the North Pole for different dates. So as you can see, From this comparison, OLR was significantly higher in August compared to September, demonstrating the seasonal heat flux variability in the polar regions. From the top left, we can see layer A and B from the same variable and same satellite, PREFIRE Sat1 and PREFIRE Sat2. But the main difference is the date and time. You can change this by selecting the layer from top and then change the date from the bottom horizontal top. And when you are done with the comparison, you can just go back to the left there, you start with the comparison and click on this gray button to exit the comparison. So now exiting the comparison, I will add another layer on NASA's historical Aqua Airs mission, which measures outgoing longwave radiation at approximately 40 kilometers spatial resolution. This allows us to compare radiation observations from different missions. I'll drag the Airs globally data below the PREFIRE, so we can see the PREFIRE on the top from the left window. Then we can see a strong correlation between PREFIRE OLR and Airs values. But PREFIREs offer a much finer resolution for each orbital swath, capturing more detailed energy movements. Let me quickly highlight PREFIRE's data structure. Each PREFIRE tier swath spans approximately 264 kilometers, consisting of 8 distinct tracks of data. Within each track, you will find spatial scenes with footprints sized at approximately 11.8 by 34.8 kilometers, separated by a gap of 24.2 kilometers. This detailed resolution provides invaluable insights, especially when compared to the course of all our measurements from Earth. In addition to the geographic projection that we have been seeing in the demonstration, so starting from December 8, 2025, you can also visualize the same PREFIRE data in Arctic and Antarctic projections. Since PREFIRE goal is to focus on polar observation, this exercise will guide you on changing the projection. So starting from here, to access these projections, you have to navigate from the top right, this Earth button. So clicking here, you can see how to choose between the desired projection, whether Arctic or Antarctic, to display the data in the polar map view. Once the projection is selected, the tool allows you to publish oral per 90 minutes, which is the average orbital duration, providing a synchronized visualization of the PREFIRE CubeSat swath over the polar regions. This capability showcases the PREFIRE mission unique ability to monitor radiated fluxes in polar specific conditions. You can see here the cross-section between the two satellites. Okay, so reaching at this point at Worldview, I want to wrap it up with the slide to highlight the impact of PREFIRE data on NASA's Worldview platform since the release back in August 2025. Showing this global distribution map, it's clear that PREFIRE is reaching a diverse international audience. Each marker here represents user locations, and this is around the world. So showcasing widespread interest, particularly in the North America, Europe, and parts of Asia. The pie chart on the right is showing more than 40 countries interested in the PREFIRE data in Worldview. So that was the last slide in Worldview. Let's go to the next slide to learn about another tool. The tool I want to show you now is Earthdata Search. So mainly for exploring, downloading PREFIRE data using Earthdata Search, which is a platform unlike any other in the world, offering unprecedented access NASA's collection of Earth science data. With Earthdata Search, you can search, explore, order, subset, aggregate, visualize, and analyze data freely and seamlessly. I will show you the step-by-step process of finding PREFIRE collections, filtering the data, and we will download some of the files and visualize it to help you in your research. So what you can see here is if you go to search.earthdata.nasa.gov, here you can see a variety of search and filtering options. You can explore hundreds of NASA missions by typing the mission name. So let's start from the top here. In the demo, I'll type PREFIRE into the search box, and this will filter the dataset to the PREFIRE mission. You can also filter results further by keywords, platform, instruments, data level, organization, or format. For today's example, I'll focus on level of the geophysical retrievals, level 2, and I will focus on NetCD update. We can learn more about the collection by hovering over the description. From here, I will open the dataset collection, SAT2, level 2, surface emissivity, which you can see here. This collection has more than 6,000 files, and you can go to the ASDC website from these URLs or open the user guide in PDF in another tab. You can also download it if you want locally or can visualize it in the browser. You can go to other related URLs, including the ATBBs and many other documents, algorithm software with also the products. Or you can open the CMR search view, like you can see here. You can look at the variables, the metadata, the usage. You can see the services. A very useful display. Now, if you want to go back to your original files, you have to click on the 3 dots on the top right of the collection that I'm pointing with. And now we are back with the files. So to refine my search results further using spatial and temporal filters, I will choose the archive projection for filtering. So on the very right here, there are some vertical bar where you can select the vertical projection. I'll choose the map projection to polar instead of geographic and draw a bounding box over green one. This filtering step isolates only the PREFIRE swaths within the blue box, reducing the data from 6,000 files more than 6,000 to 3,700. So now let's try the temporal filter. To narrow the results further, I'll select the first 5 days of September, which reduces the data to 46 candidates. At this point, I can choose to download all 46 NetCDF files directly, or I can do post-processing for the data as needed for my search. So getting to this point, I can just selecting the download the data, and then I can, it's going to give me all the URLs from the S3 bucket. You can also get access to the S3 bucket. We'll do this for the ArcGIS, or you can have a download script. If you want to access programmatically, you can download all from the buttons. You can go through the image, the browse imagery that were generated by University of Wisconsin. So all of these are great options to download the data and visualize it. Just for this webinar, I will show you how to open it on Panoply. So you'll find resources for where to get Panoply from and download it locally in your machine, and then you can drag and drop the NetCDF file that was downloaded and filtered by Earthdata Search here in this area, and then you can over to your variable, so surface spectral emissivity, and by double-clicking on the variable, it's going to open this window in the top right. You will just do very minor edits to the minimum and maximum of the color bar. So I'm using 0.81 here. There are a lot of features for Panoply, so I'll just leave it for you to explore more. You can visualize, you can change the colors, you can do advanced plotting options, you can have remote access to using OPeNDAP, for example. We can export the data on other formats like CSV. So it's really great tool to use, and this is just a quick brief of how to use it. All right, so now after we used Earthdata Search, we are going to switch gears again to demonstrate how to work with PREFIRE data in geographic information system, especially ArcGIS Pro. This is particularly valuable for researchers who need to integrate PREFIRE measurements with other geospatial datasets. GIS platforms offer unique advantages for PREFIRE data analysis. So let's dive into the GIS environment and see PREFIRE data in action. All right, so starting from here, for this demonstration, you can see Earthdata Search again on the left-hand side. And you can see ArcGIS Pro on the right-hand side. So we want to enable the analysis on ArcGIS Pro. You can access also PREFIRE using the S3 buckets, as we saw earlier. I want to thank University of Wisconsin for generating this cloud-optimized GTIP dataset for first-zone analysis and help the users to use ArcGIS for post-processing. So let's start here from Earthdata Search again. So going to the PREFIRE, and then I will select the very first collection we have here. This is for the flux, where we have the outgoing long-wave radiation. So from here, I will download all the data, but I will not actually download it. It will just give me the download links in the cloud from the S3 bucket. So we're looking here at approximately 6,000 granules. So going to the right-hand side to our ArcGIS Pro, I want to connect to the cloud. So I need to enter some attributes here. So starting with PREFIRE for the connection name. Then I'm choosing the service provider, Amazon, and then I'm choosing which Amazon server is going to be US West 2 in the state of Oregon, this one. Then making sure that the link is correct, including US West 2. Good. So I can go now to the Amazon Web Service S3 in the left-hand side and copy the name of the bucket. But as we're using Amazon anyway, I have to delete the very first section, which is calling it S3, because it's within the Amazon environment now. Then I need to get AWS S3 credentials. So clicking by this is going to generate your own credentials. I'll start with access key ID, copying it over, and then the key access, I'll copy it over as well in the access key on the right-hand side, and then I'll copy the token, and I will move it also to the right-hand side here on the session token. Paste it here. I'll just QC that everything looks correct for me before I press OK, and make sure that ArcGIS Pro is reading all of this data instantly. All of these thousands of granules can be read in no time within the ArcGIS Pro. So I'm opening the first folder from July 24th, dragging and drop the first file. It has three files in the same day. So zooming in and looking at the whole of it's in the native grayscale color. So I'm going to change this later, dragging and drop another file. This is all happening very quickly. And that was not possible before having this cloud scalability. Now I'm changing the color from yellow to red, our scheme, and we can see the differences between the native color before and after. So now I don't need the Earthdata Search, maximizing the ArcGIS Pro to focus on what I'm going to do with this data access from ArcGIS Pro. So the next step, I need to create a mosaic to start having all of this raster data within this mosaic. So my project called my project 10 are geodata days. Then I'll call the mosaic dataset name OLR. You can choose any coordinate system using the WGS 84. You can also focus on specific band, and this is a good option in case you have several bands or multi-dimensional multi-variables within the cloud optimized Jupyter. By running this geoprocessing, I will have the OLR. Now I want to add rasters. So I will just have few options to input the data. So between file, folder, or data set. To choose, we will need the folder option. So choosing it, I'll go to open all the folders that we have access to in the cloud. But to load all of them is going to take a long time. So I'll just go through. You can see the data from 2024 to 2025 here, because this was recorded later last year. So I will just select the ACS and go to the very bottom to select the recent 10 days of the PREFIRE data that was back on October. Just clicking on them, they are loaded, added to the mosaic dataset. I need to run but geoprocessing from the bottom right here takes few seconds that you are going to see all the data that we just selected from the cloud, again, in very short time. Right, this is great reaching this point. Now, we have to go through this Python function that we are going to use in the next step in our demonstration that's crucial for what most PREFIRE data on ArcGIS Pro. In the following demo that I'm going to show you, you will need this extract datetime string function to solve a common challenge when processing PREFIRE file names in ArcGIS Pro. So PREFIRE data contains datetime information embedded in the file name, but we need to extract this format in properly for our analysis. So this function takes the file name as input and parses out the datetime component. Here how it works. So first we split the file name by underscores to break it into parts. And then the datetime information is typically in the third part of the file name. The function then checks if the datetime string has exactly the 14 characters that we have in most of the files, all the files, which corresponds to the year, month, day, hour, minute, second components, and restructuring them with proper separators to be ArcGIS Pro friendly. So let's go back to ArcGIS Pro and run this code from ArcGIS user interface and see how it's going to work. Okay, after successfully generating the mosaics, and next steps in the preparing the data will be to generate the multidimensional formatting. Here is how we're going to do it. So the first, modifying the attributes as we are doing here, looking at the product name, you can see it's all empty. So I will just add, I'll calculate the field by populating it with the variable OLR. So doing this, you can see now it has all OLR. Next, I will add a new field called STD time for standard time, and I will assign a date for this. So I'm going to type here STD time, and then I'll change the data from long to date. I'll make sure that it's saved. So by closing the window, it's going to save automatically. Populate the standard time. So you can see now in the column of standard time, it's empty, it's null value. So to pull this data, we calculate the field from the previous code that I just showed you with function. So that will extract the date on time from the file name. After running the calculation, I will validate that the date time values have been correctly pulled for the record. So you can see here in the standard time column, everything looks as it's supposed to. Okay, this is great. Let's move on to the calculating statistics and adjusting symbology. So I'll move to the geoprocessing, and then I'll type statistics here, calculate statistics. We want to ignore some null values typically represented in the data. So I want to add here 0 and negative 9999, and then I'll run this geostatistics. It takes a few seconds, and then we will need the next step to update the symbology from the data that it's going to be, instead of black and white, to more intuitive color scheme such as yellow for the lower and OLR values, and red for the higher values. So to do this, you click on the color on the left, and then we'll select the color of your interest for this specific band, and this is going to reflect on their visualization instantly. Right. Let's move on building our multidimensional data. So in this step, I will define the multidimensional data using the geoprocessing tool, build multidimensional data set. As you can see here, I'll select the mosaic data set that we just edited, set the product name to OLR, and use the temporal dimension standard time that I created earlier. Once I run the tool, so ArcGIS Pro will create a new tab at the top horizontal bar labeled multidimensional. So once this happened, you can see here it just populated the multidimensional. Let's explore it with a new dataset ready. So I can now choose individual layers and analyze how OLR varies over time. So using the temporal profile tool, it will open a new window here on uh, the right panel here that allows me to create a customized time series. So for this demo, I'll select a polygon over Greenland to analyze OLR trends in this region. So the tool will display the maximum outgoing radiation over the area, as you can see here, showing clear diurnal variation for every single day on the data set. So to summarize the data further, I will aggregate the OLR values daily using maximums. So for example, here you can see that by clicking repression, so I'm changing, from hourly to day. So I'm going to change to 1 day aggregate. And then you can see for October 4, year 2025, we have a record high OLR value over Greenland, the area that was selected on the top. And you can change it, of course, with a shapefile. This is just for the demo. We can expand it in several directions. If I switch to analyze mean values instead of the maximums, we can observe a significant drop in OLR on the October 3rd and 4th. A trend worth investigating further. So this workflow enables detailed spatial and temporal analysis of PREFIRE, outgoing longwave radiation data, helping us gain invaluable insights into Earth's energy budget, especially in critical regions like the Arctic. All right, so now I think we got to a very great point, seeing how to work with PREFIRE data on ArcGIS. We will move on to another tool that is pretty famous in the government. So subsetting PREFIRE using OPeNDAP. This is a powerful tool that allows you to access specific portion of a large data set without downloading the entire file. So with OPeNDAP, you can select the exact variables, spatial regions, or the time ranges that you need for your analysis. So in this segment, I will show you how to use OPeNDAP to subset PREFIRE data, walking step by step through the process to exact precisely what you need for your analysis. So let's go to Earthdata Search again to see how can we use OPeNDAP subsetting from Earthdata Search. We'll be using Harmony OPeNDAP subsetter. So this service also called OS for demonstrating Harmony, allowing you to specify temporal ranges or spatial ranges like easily like what we did before on Earthdata Search by entering them in the top left or interactively using the graphical selection tool like we did earlier. For this demo, I will focus on subsetting data by variables only to show how efficient you can customize your data set for your research purpose. So here I'm selecting Customize with Harmony, and then I'm selecting HOS or Harmony OPeNDAP subsetter. And then I will move to select the one variable. And in this case, I'm going to select mean. As you can see here, this is the mean surface emissivity. And I'll choose NetCDF4 as the output format, and then I will just click download. And after running the Harmony request, like what we just did now, it takes approximately a minute to process all 10 files that were selected earlier. What happens during this process? That the Harmony service queries the database to retrieve the files I selected. Then it fetches the OPeNDAP URLs that I demonstrated earlier. Once these URLs are obtained, Harmony executes Python code on Amazon Web Service Cloud infrastructure to process and subset the data using the specific OPeNDAP links. Harmony extracts only the variables that I selected, and it processes the data and generates new subset NetCDF files where you will find the data. It will pop up shortly. So the Amazon Web Service Cloud, it's in the US West to Oregon. So by the end, finally, like Harmony product, like the products, the URLs for the customized subset files will be available and ready now for visualization and downloading based on the request that we submitted. So we can see here it's in progress, 27%. We can select the first link we have here by clicking on it. It's going to download the file locally. So I'll download this in my downloads folder. So here's the NetsDF file, 8.5, 8.2, 8.25 megabytes. And then I will open a new tab and I'll go to my HDF 5.hdfgroup.org. This is pretty much very similar to Panoply, but the nice thing, you don't have to download it. Just drag and drop the file here and you can see you can see the file here with all the variables. It's only one variable, emissivity mean that we selected. The platform will read the file and we can observe that OS has subsetted the data and displaying only the surface emissive. So there are many dimensions you can see here, including spectral, spatial, temporal. So I'll let you all navigate, depends on your visualization needs, which one you need to have on the x-axis or the y-axis. There are a lot of other features and export in different formats that we can do using my HDF file. All right, this is really briefly the subsetting using Harmony OPeNDAP. Now, moving on to the last piece or demonstration will be for the programmatic access. So we'll discuss how to access the PREFIRE data programmatically using OpenScapes to I2C platform. I'll walk you through these steps and demonstrate how this framework simplifies data exploration for PREFIRE mission. All right. If you are new to the cloud, a lot of people are, let's just, like we want to learn more. You're looking for more support for programmatic access in the cloud. What you will think of. I will encourage you to connect with the OpenScapes group. So what is OpenScapes? OpenScapes is an open source approach designed to help researchers connect and feel empowered in conducting data science programmatically in the cloud. So in my mind, it is a community of practice, like a cohort-based program that facilitates team problem solving. We offer earthaccess, a Python library for NASA earthaccess, and we will use it today in our demo. I will talk more about it. If you are new to the cloud and want to learn more, NASA-OpenScapes, this link in the bottom, will help you learn more about them. Please add it to the link, Elizabeth and Jennifer. So from here, I will take you to ASDC's GitHub repo. So this is where we have a folder for each mission at ASDC. Of course, I'll go to PREFIRE because today we're going to go through this new Jupyter notebook in the bottom. And we have several more. I'll let you all explore them. But for today, we're going to focus on the cloud variables. So visualize some micro-physical and macro-physical cloud properties from PREFIRE using earthaccess. This tutorial was developed by Alex Ratovich from the satellite mission support team. So focusing on some Python libraries, reading to some functions that's going to read the cloud properties. So effective cloud particle effective diameter, cloud optical depth, and cloud top pressure in hectopascal. Then we would use earthaccess library. And by clicking this link in the reference, what is earthaccess, you can read and learn more about the Python library here. It's open source, means you can collaborate also. So that was born in NSIDC. Luis Lopez was the first person who initiated this. And it's a great tool that facilitates a lot of developing that we used to do before having this Python library. All right, so now walking you through, so define some functions to read through the short name of some attributes in the database, like concept ID of the collection. So we are using PREFIRE SAT2 today. Then how we want users access to filter the data spatially, temporally as well. And then how to download the data file by file. When we'll give you a quick demo showing you how to remove the downloaded file and how to plot the data in orthographic projections. So let's download the Jupyter notebook and have it downloaded locally, so we can move on and use it for our demo. So I'll open a new tab here and let's get started. So first I'll go to 2i to see. This is the environment that I'm going to be using as a Jupyter Hub. If you are familiar with Jupyter Hubs, you'll find a lot of similarities of how it looks like. So we'll find notebooks, Python in the top, and then the console, then the terminal if you want to type anything. So what I'll do next is I'll create a new folder on the left-hand side. So from the top here, this little button, and I will just call it webinar 2025. And I'll open this folder and I'll just drag and drop the Jupyter notebook that I just downloaded. And I'll just double click and open. So first, the prerequisites, we have to download these libraries. So then importing them, then reading the first function we have here for reading the variables. And then we're going to start using earthaccess. So by clicking login to earthaccess, putting here my Earthdata login, Lourdes mentioned earlier how to have Earthdata login. So I'm going to go to a new tab to show you. So we'll go to urs.earthdata.nasa.gov, and this is where you can register. But for me, it's going to open my profile right away. So you can just click on register to have Earthdata login. Then define some functions to convert from the short name and the version, which is PREFIRE set to level 2B cloud product version R01 to a concept ID. This is a nice way to convert it and pull it from the database. It can help you also in the Harmony programmatic access as well in the future. All right. So what we will need to do next is to use earthaccess library. So here's the short name and the version and the year 2024, and then focusing on the month of September 1st. And start date and date, you can customize it here. The end date is 6 and the start date is 0. So we're looking into 6 hours. The spatial bounding box here is important also to filter. So we're using from 60 to 90 north and from negative 180 to 180. So by running this cell, we'll start downloading the files one by one. Have them here on the left-hand side. We have 4 files only with this filtering that we did. Also, you can delete them, remove them, the netcdf files, and download them again in one step. The old or granules again and get them ready for plotting. You have a couple options. So this function really is going to read each PREFIRE file using your existing read function that was in the very top. We'll find valid time bounds by skipping field value -9999. Create proper data masks using the actual field value from the data, and also extract valid data points based on the mask. Generate orthographic plots for each cloud parameter. So you can change between Arctic or Antarctic just by changing the 2 lines from the CRS that were defined in the description on the top. So from here, you can see the orthographic plots for the 3 variables and block projected over the Antarctic, but you can change this, as I mentioned earlier. And you can also change a lot of things in the future, like for post-processing, you can integrate some of these plots in the same plot, for example, you can do further analysis. If you have any issues, please reach out to us. If you have any specific case or aggregation or post-processing that you're interested in, please reach out to us. I'll be very happy to help you um, using a lot of our pre-existing tutorials. And even if it's not there, we can develop something for you. Also on the left, you will see that it's exporting a lot of PNG files. So if you want any of these plots of these variables into your report or send it by email, whatever, you can just copy it from here and add it there to send it. So cloud optical depths, cloud pulse pressure in Pascal, or cloud particle effective diameter in microns. So that was the end of my section. I'll give it over to Elizabeth to give you more information about PREFIRE Resources. Thank you all.
Well, Hazem, that was a lot, and we really appreciate you sharing your knowledge about these tools, services, and weaving in the OpenScapes part as well. As we conclude our session, I know time is tight, but I do want to highlight several valuable resources that can enhance your ongoing work with these data. And I do want to remind you that, as Jennifer has done throughout this session, that we do have the Zenodo. She and Joseph have also been sharing out links throughout the session. Next slide. We also have an abundance of resources at the ASDC on our website, so I encourage you to check those out. You'll find product descriptions, ATBDs, validation reports that really help break down the science behind the data. So please check those out. And again, as Hazem mentioned, reach out when you've got questions. Thank you for moving me quickly ahead, Hazem. Hazem and others developed the story map, which is a great one-stop shop for all things PREFIRE. So this is linked in that Zenodo, so I want you to check that out. That's a story map. Next slide. And very quickly, once again, want to remind you about the forum. You can post questions on your own. You can search questions, but to post a new question, you will need your Earthdata login. Next slide. And then reaching out directly to us is always a possibility. So here are our email addresses. Again, these are in that Zenodo as well. And so we just look forward to connecting with you. And I did want to leave us some time. We have 8 minutes left for Q&A. So thank you so much to Brian and Hazem. We're really blessed in our community of practice and potential to have you there with us. So thank you. And Jennifer and Joseph, thank you for hosting us.
Sure. Thanks so much, Elizabeth. We now came in. I don't know. A lot of people are probably logging off, but in the event that this person is still here, how does the PREFIRE mission through far infrared, and Brian, I think, is logged off, radiation measurements over polar regions help reduce uncertainties in Earth's energy balance? And how do NASA's ASDC tools, such as Earthdata Search, Worldview, etc., support access to analysis and application of this data in climate research? So it's two parts. How does the PREFIRE mission, through its far infrared radiation measurements over polar regions, help reduce uncertainties in Earth's energy balance? Part one.
Okay, so this is so we were showing today, focusing specifically on the outgoing long-wave radiation. First of all, PREFIRE mission is including two CubeSats. So we have two observations that are validating each other. They are crossing each other's. So this is one part that is reducing the uncertainty. Another part of reducing the uncertainty will be through the resolution, the very high spatial resolution, when we are looking at 11 kilometer by 30 kilometer. That's very fine resolution compared to AIRS, for example, aqua AIRS, outgoing long wave radiation, which is around 40 kilometer resolution. So the spatial resolution helps us also enhance our outgoing longwave radiation models. So this is one part. How the ASDC tools, such as do you want to take this, Elizabeth?
So, in terms of how do these tools support, well, and let's clarify. One of the things, part of this question said, how do the NASA ASDC tools, such as Earthdata Search, Worldview, and Python-based Jupyter notebooks, support access, analysis, and application of these data? So these aren't necessarily ASDC tools, right? So these are part of this suite of tools are part of a much larger. And Jennifer, you could probably address this with much better explanation than I can. But in terms of NASA's Earth Science Division, the suite of tools that are made available from a much broader group of funding than just the ASDC alone. But we certainly we make our data available in those tools to support the access and analysis and application of those data. But I will say, in terms of the analysis part, that gets a little tricky in that Python has identified the Jupyter notebooks really do enable the analysis part, which is really great. Earthdata Search and Worldview, they don't they're very limited in the analysis part that they're able to support the user in, but certainly access and visualization, they can provide support in those areas. But in that graphic that I showed, I think it's called tools that you can use or something like that. It showed which tools enable different kinds of functions for that. So I encourage you to take a look and see. It also includes, specific to climate research, which of those tools offer data that are aligned with climate research. So I think that was a question from Erica. Erica, if you're still there, do take a closer look at that link provided and see which tools are accessing more climate-related data for the different types of analysis or access that you're looking for.
Yes, that's a great response, Elizabeth. And I would just echo what Elizabeth has been saying and add to it that Earthdata Search is an ASDIS enterprise-wide data discovery and data access tool that is going to allow the user access to not only PREFIRE data, but also access to the other data holdings within our additional 10 discipline-specific data centers. And so if you're looking for PREFIRE data and you also wanted to pull, data from another data center, you could do so by using Earthdata Search. And so you would, be kind of following the steps that Hasm provided earlier, specific to PREFIRE, but then you could add, your additional data sets that you may be interested in for your research or application. And then the same is true for Worldview, again, not specific only to PREFIRE, although it does visualize a smaller subset of NASA's total Earth science data holdings. I would say it's over 1,000, data imagery layers, which is not even close to all of our data holdings, but certainly is great for a quick visualization of that particular data product, which is, you saw a little snippet of that earlier within the webinar today. Just as I was trying to get off, the question came in. I'm so sorry about that. But let's do another quick look here, since we are technically not at time. And for those folks who logged off early, if you have any colleagues who did, they'll be able to hear the response to the question, because I have not shut down the recording yet. And so hopefully that's helpful in some way.
Well, and I did want to mention NASA Giovanni. Now, while pre-fire data are not available in that tool, that is an analysis tool that is quite useful. I know HASM has used that with some of our data. Moppet data, Miser data, I believe, are also available in that tool. That tool is available from a different data center, from GESDISC, but so if you're looking for analysis tools, there's also Panoply, which is another tool that NASA makes available, and so there are several different options. And one we talked about Worldview. Worldview just recently launched a time series plot. Not for all data sets, and I think it's still being beta tested, although I'm not sure where we stand with that. But for a quick view analysis, that's a great option too. So, there are some options there for analysis, and we're really excited about what the future holds for these enterprise-wide tools. And thank you, Jennifer, for adding your part. You added a lot of value to that response, so thank you.
You are quite welcome. All right. Let me see if there are any additional questions. I don't see any additional questions at the moment. And so with that, we are going to log off from the audio component of this afternoon's webinar, and I'll keep the virtual space open for an additional 10 minutes. All right. So thanks so much, everybody. Thank you all. And with that, have a wonderful weekend.
You too.
All right. Take care now. Thank you. Thanks, everybody.